Hello, in this presentation we will begin our discussion about correlational studies, which investigate how certain variables are associated. Specifically, we will learn how to use and interpret scatter plots, how to calculate and interpret correlation coefficients, and we will discuss the assumptions that are made when such coefficients are used. Many research projects are what we call correlational studies because they investigate the relationships that may exist between variables. Before investigating the relationship between two quantitative variables, it is always very helpful to create a graphical representation that includes both of these variables. Such a graphical representation is called a scatter plot. Let's say that we would like to investigate the relationship between students' achievement motivation and their GPA. The table on the left includes a small group of individuals for whom we recorded the GPA and their score on a motivation scale. GPAs can range from 0 to 4, whereas motivation scores for this particular scale may range from 0 to 100. Individuals in this table were ordered based on their GPA, starting with the students with the lowest GPA, which is 2.0, and ending with the student with the highest GPA, which is 4. Just by looking at the data set, we can see here that in general, as GPA increases, motivation scores also increase. However, with a real data set, which may include hundreds or even thousands of individuals, we cannot detect a pattern simply by looking at the numbers. Therefore, a very useful strategy is to represent graphically the two variables to illustrate the relationship between them. Such a graphical representation is called a scatter plot. The graph on the right is a scatter plot for two variables in our dataset, GPA and motivation. For every individual in our dataset, GPA values are represented on the horizontal axis and motivation scores are represented on the vertical axis. So each dot on the scatter plot represents one individual from the dataset. Their location on the graph depends both on their GPA and motivation. Individuals with higher GPAs are located towards the right margin, and individuals with higher motivation scores are located towards the upper margin of the graph. For instance, Sam has the lowest motivation score and the lowest GPA. There are two other students with the same GPA, like Joe, but Joe has a higher motivation score, so the symbol for Joe is located at a little higher up. Tammy has both the highest GPA and the highest motivation score, so the dot that represents Tammy is located in the upper right corner. Scatter plots are not meant to be used in so much detail, though. When we have hundreds of individuals in a data set, the scatter plot has hundreds of points, and we cannot identify each one of them. The purpose of a scatter plot is to provide a general illustration of how the two variables relate to one another, to help us determine whether there's a general pattern. In our example, we can see that in general, as GPA increases, motivation scores also increase. One of the students doesn't seem to follow this general pattern though, and this student is Mary. She is one of the students with the lowest GPA but has the maximum score on the motivation scale, so she is an exception or an outlier. Just like with any other types of graphs, when interpreting scatter plots, we must try to identify general patterns as well as the outliers that do not fall into that pattern. Patterns can be described in terms of direction and the form of the cluster of points, as well as the strength of the relationship between the two variables. Let's first talk about the direction of the relationship that we're investigating. We say that two variables have a positive association or a positive relationship when higher values on one variable are associated with higher values on the other variable, or lower values on one variable are associated with lower values on the other variable. One example of such a relationship is the relationship between students' achievement motivation and their GPA. As we can see in the example on the left, when students' motivation increases, their GPA also increases. The arrow indicates the direction of this trend or the direction of the motivation variable as GPA increases. In contrast, we say that two variables have a negative association or a negative relationship when they go in opposite directions. For instance, the relationship between student GPA and the number of unexcused absences. In general, students with lower GPAs have higher numbers of unexcused absences, and as GPA increases, the number of unexcused absences decreases. This example is illustrated by the scatter plot on the right side, where the arrow indicates the direction of the absences variable as GPA increases. The form or the shape of a scatter plot is also very important in describing the relationship between two variables. The example on the left illustrates a linear relationship. This means that the scatter plot describes a straight line. The plot describes a line because the y variable, which is in this case motivation, increases by approximately the same rate when the x variable changes by 1 unit. However, sometimes the scatter plot describes a curve rather than a straight line. This is because the rate by which the y variable increases is not the same, and it may even start decreasing after a certain point. The example on the right describes a curvilinear relationship between the variable age and the variable working memory. We can see here that working memory is increasing throughout childhood and adolescence, becomes relatively stable during adulthood, and then gradually decreases after the age of 50. Now, this is just an example based on simulated data, so you shouldn't start worrying about your working memory now. Scatterplots can also provide information about the strength of the relationship between the two variables. When the relationship is strong, the slope has approximately 4 to 5 degrees. As the relationship loses its strength, the slope approaches either the y or the x-axis. When we are investigating the relationship between two variables, the strength of the relationship is a crucial piece of information. Relying simply on the interpretation of scatterplots is too subjective. We need more exact evidence, and this evidence is obtained by calculating a coefficient that measures the strength of the relationship that we are investigating. Correlation coefficients measure the strength of the relationship between two variables. The formula presented here is for the Pearson R coefficient. For each individual, we calculate the difference between the x and the y variables and the mean. These differences are divided by the standard deviations and then multiplied. The results obtained from every individual are added up and then divided by the degrees of freedom, which is n-1. You are not going to have to do any of these calculations by hand unless you really want to, but statistical software computes correlation coefficients for us. It is important, however, to remember that correlations are based on the means and standard deviations of the two variables. It is also important to know that the Pearson correlation coefficient must be used only with quantitative variables and relies on the assumption that the relationship between them is linear. The notation that we typically use for the Pearson coefficient is the lowercase r. Correlation coefficients can range from -1 to +1. When this coefficient takes the value 0, or values close to 0, there is no relationship between the two variables. When the coefficient takes values larger than 0 or positive values, the relationship between the two variables is positive. When the coefficient takes negative values, the relationship is negative. The closer the values get to 1 or -1, the stronger the relationship between the two variables. When interpreting correlation coefficients, we have to make the distinction between strong, moderate, and weak relationships. Typically, regardless of the sign, values lower than 0.3 show that there is no relationship or a very weak relationship between the two variables. Values between 0.3 and 0.5 show a weak relationship, whereas values between 0.5 and 0.7 may indicate a moderate relationship, and values larger than 0.7 show a strong relationship. These are just rules of thumb. They are not set in stone. The interpretation of correlation coefficients may also depend on other factors, such as the sample size, the area of research, and so on. Based on the criteria that are typically used to describe correlation coefficients, we can say, for our example, that there is a positive linear relationship of moderate strength between achievement motivation and GPA. These scatter plots illustrate what the relationships look like at different degrees of strength, so for different values of R. And we can see here both positive and negative relationships. We can see, for instance, that for a correlation coefficient of 0, the points have no direction. The shape is almost round, and we cannot fit a line on the graph. As the correlation coefficient increases, the observations get closer together and begin to describe a line. This line is hard to detect when the relationship is weak, smaller than -0.3, for instance, but becomes more and more clear as relationships become stronger. When we calculate correlation coefficients using statistical software, we can also obtain a probability coefficient. We usually call this probability the p-value, and it shows the probability that the relationship between the two variables is equal to 0. Therefore, when the relationship between the two variables is strong, this probability is very small. The higher the correlation, the lower the p-value. Correlations are typically considered statistically significant if the p-value is lower than 0.05. The researcher has the liberty to decide what a reasonable cutoff is, but this is the value that is typically used in social sciences. We call this the alpha level, and we must report our alpha level when we report our results. In other fields like medical science, estimations must be much more precise. There is less room for error, so the alpha level may be lower, like 0.03 or even 0.01. When using and interpreting correlations, it is very important to make sure that we know a few facts about them. First of all, in correlation, the order of the two variables that we investigate is not relevant. The correlation between motivation and GPA is the same as the correlation between GPA and motivation. This order is not important when we formulate the research question or when we conduct the statistical analysis. Furthermore, correlation coefficients are only showing that the two variables are associated, and not that one variable explains or produces a change in the other variable in any way. For instance, we may find a high correlation between GPA and motivation, but this is not enough evidence to say that higher motivation leads to higher GPA or that higher GPAs increase students' achievement motivation. There are other statistical analyses that are used to try to provide evidence of causality. Only a correlation is not sufficient. All we can say is that high GPAs are associated with higher achievement motivation. Regardless of how the two variables are measured, the correlation coefficient always has values between -1 and 1 and is therefore measured in the same way. As we mentioned before, positive values indicate positive relationships and negative values indicate negative relationships. The Pearson correlation coefficient is based on certain assumptions, and we have to make sure that we meet these assumptions when we're using this coefficient. First of all, both variables must be quantitative. There are other types of coefficients that can be used with ordinal variables, but the Pearson coefficient can only be used with quantitative variables. Furthermore, it is also assumed that the relationship between the two variables is linear. Because the correlation coefficient is based on means and standard deviations, it is not robust to outliers. It is strongly affected by extreme observations. We call these individuals influential observations because they have a strong impact on the correlation coefficient. For instance, in our example, we can see the correlation coefficient is 0.62 when the outlier is included in the analysis. However, when this outlier is removed, the correlation coefficient increases to 0.89. This is one case. When included in the analysis, it reduces a strong relationship to only a moderate relationship. In our example, this case makes a big difference because we only have a few individuals in the dataset. As a general rule, as the size of the data set increases, the influence of extreme observations decreases. When describing the relationship between two variables, correlations are just one piece of the puzzle. This information is necessary, but is definitely not sufficient. Other analyses should be conducted as well to provide more information. In this presentation, we discussed how to use and interpret scatter plots, how to calculate and interpret correlation coefficients, and the assumptions made when such coefficients are used. I hope that the explanations and the examples provided were helpful.